So guys, let's talk about laminar flow, transient flow, turbulent flow. They depend of course on the velocity. More velocity means more chaos, less velocity means other chaos. Viscosity, well, viscosity is, let's say, the property that goes against flow. So if we have high viscosity, we will expect laminar flow, very ordered. And if we have a high low viscosity, we will expect very disordered movements and so on. Diameter, why? Because the diameter will increase velocity, and not only that, if you increase the diameter, you will expect more disorder. And the density of the fluid, this one is tricky, we're going to talk about it later. But first things first, velocity. Increasing velocity makes more disordered flow, that's true. Hopefully you see when you have open the water of your, sink. If you do it slowly, you will have a very nice jet. But if you open it, you will have like a super chaos and this is very fast and so on. And you will see, of course, this is order flow, this is disorder flow rate. So when you increase velocity, you favor turbulence. If slow, you may even model the flow as many layers. So imagine here goes the flow, and you can see that actually you have many layers. The blue layer, the cyan layer, the green layer, the yellow layer, the light red layer, the dark blue layer, and so on. So you could actually model it as very fine layers moving as blocks. Reynolds number actually here is very small, which means it's laminar. For the other side, guys, if we will have a very extremely high Reynolds number, which we don't have here, but let me show you, this will be a chaos. You could not model this as a layer. Now viscosity, when you have more viscosity, you will in general need more shear stress to make the fluid flow. So if you have not that much flow, you will expect no turbulence. For example, this viscosity is very high, and this viscosity is very low. So which do you think is better to model? Would you rather go and model each one of these random, very chaotic flow waves, or would you prefer to model this? Actually, you could model this with a cosine or sine function very easily. This one, well, a little bit maybe. This one is already very chaotic, and this is very chaotic. So hopefully you get the idea that as viscosity increases, we have less turbulence. Now, pipe diameter. Recall, Reynolds number is rho, velocity, density divided by viscosity. So more density, more diameter, more Reynolds number. But larger diameters allow more space in between, so you will expect more disorder. If you recall from your profile list, you will have very static flow here and very chaotic flow here. So if you make it every time longer, you will expect something like this. This is high velocity, therefore this will be a lot of turbulence, and expect low turbulence right here. So the more you send away the walls, the more chaotic the flow will be. So for example, imagine a very small diameter like this one. The walls are so close that you could model this with layers, because you will have many flow here, and you could say it's laminar flow. But be very sure, guys, that diameter affects velocity, so that's kind of tricky. The Reynolds number applies in general, but if you are using a cylindrical pipe, expect that if you increase the diameter, you will lower a lot the velocity. So what I told you actually is as a factor of 2, and this will be as a factor to the power of 2. So if I make it twice the diameter, I will make it 4 times more in the velocity, because this changes. You recall, let me show you here, the velocity of A, diameter of A to the square equals velocity of B, diameter of B. So if you increase the diameter, you need to decrease the velocity. If you increase the velocity, you increase the diameter. Good. Finally, density of fluid. More mass per unit volume will, by definition, have more disorder. This might be counterintuitive. You will say, no, more mass is more well packed. But actually, no, guys. Remember, we are talking about molecules, so more means more disorder. Anyway, let's analyze this in the Reynolds number from the next one. So, as I told you guys, these are the common examples, and these exact variables are used in the Reynolds number. So we can use the Reynolds number to know if laminar, transient, or turbulent flow is present. So for example, this is the typical example you get in transport phenomena. You have the cigarette here, and it starts flowing very nice. Actually, I love this flow, it's so straightforward. And then it starts going a little bit chaotic, but not that chaotic. And finally, you get this super turbulent flow, which is relatively easy to model. So you want to avoid this transient flow, either laminar or turbulent flow. See you in the next video to understand the laminar flow more deeply. This was a free preview. You want to get full access, go to my incompressible flow course. The link is in the description of the video. You will get all access. Not only that, you get a very straightforward, user-friendly interface. So for instance, you were analyzing or studying pumps, you have it here, the pump block, and then you have the sections. If you were, for example, studying the types of pumps, you can go here, and you have all the classes right here. Not to mention that you also have introduction and conclusion of every one of these. So for instance, if you were studying positive displacement pumps, the video is right here. You were studying positive displacement pumps in rotatory and reciprocal are also included here. Centrifugal pumps, which is a very important topic in this course, you have it right here.